check yourself by writing the dynamics equation. So looking at the sum of the forces in the theta direction equals the mass times the possible acceleration in that direction. Let's do it. So we have a positive n minus mg cosine theta, and that has to be equal to the mass times r theta double dot plus 2r dot theta dot. We confirmed earlier, we concluded that theta double dot was 0. And more recently, we confirmed that r is unchanging while we're still in this pseudostatic condition. So r dot is 0, which then zeroes out the Coriolis term, even though theta dot's non-zero. Okay? So rather than just saying a theta equals 0 and going at it, this just confirms it. And so therefore the normal is as we would have expected, is that mg cosine theta, and that mg cosine theta term then drops in when we equate this critical friction force with these terms, and it drops into the denominator. And notice the masses now disappear. And there's a generalized expression given the theta dot value, given the theta dot and the 1.5 feet in the problem. And so then we could then figure this out using 50 degrees there. So finally, mu s, if theta equals 50 degrees, should calculate out to be 0.54. Okay, good. Okay. Is that right? Yes.
Interesting is that simplifying to like the static coefficient of friction equals tangent theta minus just a factor.
Minus just a factor.
So it's really close to our original definition.
Yes. As a matter of fact, thank you. Remember I talked about how you could experimentally determine a friction coefficient by just taking an object such as this and just slowly tilting it up until it starts to slip, even on a shirt, okay, right? And that critical angle at which it starts to slip is the friction angle. The tangent of that is your friction coefficient. Okay? So, if you, I'm glad you mentioned that, if you separated these terms, you can see that that gives you a tangent theta, which would be, if you did this problem very slowly, subtracting that term, and that last term there is the one that is affecting the friction coefficient because of the dynamics. Because of the dynamics. Yeah. There's kind of a dynamic kind of a, you would sort of expect, if I put this on a fast rotating arm, you'd kind of expect this thing potentially could fly off, right? The other way. Does it make sense? So there's kind of a dynamic force, effective force there that plays into this that then actually detracts or takes away from what the static coefficient would be if you weren't in a dynamic environment. Yeah. Well, also keep in mind this was at what, 1.5 feet, that value?
Right.
Where did we get that 13.5 from? See, it's got the R in there and it's got the rotational speed built into it. Now, if I wanted to take the time with you, is we could come back through, we have the equations all nicely laid out here, we could come back through and leave these terms in there. How much work would that be for us to do that? Not much work at all, is it? It's just right here. I think it's worth maybe taking a moment to glance at that. Just leave this as r theta dot squared instead of using the 13.5. Let's track it. Drops right in here, r theta dot squared. The negative's already accounted for here. So right there, we can just drop in r theta dot squared. And I don't think there was anything else that was critical or specific to this problem then, is there?
Calculated
There it is.
that value. How much of a factor was a rotational term in there? I mean, was it a big contribution? Was it a fairly small one?
Well, that's worth taking a look at. Good questions. And this is the value of doing these problems with someone else. Like, you know, we do these in class and we get several people thinking on them, but when you folks are studying with each other, oftentimes you find these kind of insights as well. So, and I've encouraged you to do that before, is work with each other. Not so you can just copy somebody else's work, but to get this insight going. Okay, so what is this term? If that was the 13.5, what's the separation on these? What's our tan theta? Tan of 50 degrees. That's getting up close to square root of 3 in value. So what's tangent of 50?
1.19.
1 point what?
191.
19, okay. And then what's this guy? With our 13.5 in there divided by 32.2 cosine 50.
0.27.
How about, excuse me?
0.27.
If it doesn't go that way.
0.6 something.
Excuse me?
Hold on.
Something screwy.
Yeah.
1.5.
That's 0.6.
Arithmetic gets us all.
Yeah. This calculator can be stupid sometimes.
It's not the calculator.
It's .652.
It's the human factor, huh?
It was Jake, actually.
Yeah,
It was
Jake did it.
0.652.
Right down here, 0.65?
Yeah.
So quick.
Okay.
And then that comes out right.
Yeah, so you can see that's pretty significant. Okay. Now, this bothers me a little bit. Of thinking of the way I was describing to you, you let this tilt. Imagine there was no velocity. And you just gradually tilt it up, it's going to come up and give us this value.
There's a dependence inside that
Yeah.
data on the speed.
I think something's fishy. Yeah. Yeah, Alfred.
Okay, if you want to, say you wanted to have a coefficient of friction such that if you turn the thing fast enough that it won't slip by the time it gets to 90 degrees and it'll still be going through.
Yes.
I'm noticing both of those terms freak out at 90 degrees,
Oh, yeah.
but at the same time you could just say like the downward v squared over r acceleration is going to be g.
If
Something
the
like
object
that.
becomes vertical. I mean,
Right.
if the mass sitting up there gets up to here,
Right, if you
it's
didn't
like
want it to
totally
slip
stuck
out.
to it. Yeah.
Yeah, it would slip off the end before
Right.
it reached.
Yeah. So what I want to point out to you is let's look in the back of the dynamics book for a second, and you can find these in statics text as well, most engineering text, where you see coefficients of friction summarized. Here we are. I'll back off here on the telephoto a little bit.
What page is that?
I'm back on 707.
Oh, wow.
And notice these coefficients of friction are all less than 1. Rubber tires on smooth pavement, 0.9.
No, so
Now,
notice for the
see,
kinetic,
yeah.
the dry steel on steel is less than greasy steel on steel for kinetic.
Yeah. But what I want to point out to you is if you think about this, we can't just talk about that little experiment I was talking about the tangent of the angle. It's not gonna work properly. Because if you think about the concept of that normal force and the friction force, and that resulting in the friction angle there, okay, that combination, that you're not going to get above 1. So let's just leave it at that right now. And
I think I know where that might get 1.19. It's the fact that
yeah,
since we're in a polar coordinate system, that in a rectangular, where you'd expect the tangent theta to work out, in a rectangular, n does not equal mg cosine theta, because there is some acceleration upward, right? Or wait, downward, I'm sorry. Because there's some addition, because acceleration is inward, right? But that means there's a component downward. So in the xy, then n would have to have some additional component to compensate gravity. More than.
believe what you're saying is correct.
Okay.
So let me just leave it at that. There's something fishy here by this fact value. When I saw that 1.19, I knew something was not right based upon my knowledge of surfaces, like shown in that table chart right there. Okay, so we'll just leave it at that. Okay.
Well, I guess it does kind of show that speed increases the effective coefficient of friction, I guess, if you wanted to call it that.
Yeah, or it lessens it. Be great, because it was negative. It was taken away from the tangent reading.
Well, yeah, but it goes higher before
Yeah.
it slips than it would.
Yeah, than it would normally. Yes, correct. Okay. Let's grab another problem. Possibly try one in a different, in normal tangential coordinates. Let's try one like this, and I've partially drawn a sketch here. This one up here, this is on page 150. This one up here at the top is assigned in your homework. It's a rotating cone, and you place an object inside that rotating cone, and you want to figure out the range of values of omega when this is in rotation, the range of values of omega that will allow that object to remain on that surface and not starting to move. So there's going to be a minimum value of omega where the object would want to impend to slide down, and then you could imagine a higher value of omega where that object wants to scoot up and out. Okay, so that's one that's in your homework. I'm going to go through the next problem, which just reverses the surface, but if you take notes on it, just try not to use those notes to do your problem, okay? Sort of short circuits your learning process. So here's the problem. I'm just going to make this a little big here so we can see it nicely. Yeah, let's see if I can get that to stay right there. Okay, that's pretty good. I think it'll stay there. So I've drawn a pretty decent free body diagram here. Again, we have this disk rotating, and the mass is placed on this surface. And this one, we assume the angular velocity very gradually changes. And what we're trying to figure out is the maximum angular velocity allowed to keep this object from then sliding down and off the surface. So this problem, we only have to work at one side of the problem where it's slipping down and off, whereas the one on your homework, you have to find that range of values. Okay? So there's a pretty good free body, and we'll go ahead and draw that. And I think we'll go ahead and tackle this using normal tangential. Everybody understand the question? Okay. So let's use this equation now. And we have the object sitting on this surface, and the incline of the surface is 30 degrees, is that right? And here's the mass sitting on there. It's weight mg. It's prescribed normal. 30 degrees being our theta angle, right there. If we use normal tangential, normal is going to point back towards this. Well, actually, no. Here's the axis of rotation.
So your normal points towards the axis then?
Correct.
And then your,
Well, here's the key.
then is your t-hat component coming towards you?
Yeah. So here's the deal. Very good observation. What we want to do is think of, when you're doing these kind of problems, think of the physical path of this mass. This path is this way, isn't it? It's doing that. So it's a circular path. And so pointing back towards that center of curvature of that path is the direction of that unit normal. And as you just mentioned, then, and it won't matter if this is turning counterclockwise or clockwise, depending on which way you're looking at it. And the way I oftentimes do that, you'll see in the book, they'll show something like this for omega. Well, sometimes that's not real clear. So what I do is I imagine my right hand, and this will be useful later in the course, my right hand doing the rotation, and my thumb points in the direction of that. And so then oftentimes I'll draw a double arrowhead indicating the sense of that omega. This will be very useful later in the term, because that is really a vector. That omega is in a vector direction, as you've seen in fourth term calculus or so. Okay. And we'll be using them in vector form later. Okay. So we have the normal. So then the tangential is coming towards us, as you said. Okay. Now, the way I do that is if I wanted a vector that went into the board, I'd put an X. That's kind of like the tail of the arrow. If I want the tip of the arrow, something coming towards me, I put it like this. So this spot right here, that's the head of the arrow. It's coming out of the board towards us, and that's going to be our t-hat direction. Okay. Everybody understand it? Feeling good? Okay. If we look down, this would be an elevation view. If we did a plan view, looking down on the object, here's our mass, our normal is pointing in, and our t-hat is pointing this way. And the rotation is like that. It's oftentimes useful to do both sketches. So now when you write your equations, what I think might be good is let's write the tangential equation first and just take a peek at it. The sum of forces, oh, did I finish my free body? missing the friction, right?
And the log wants to go down, so the friction's going to be up the
Okay. So we'll draw our force vector up the ramp, up the incline. Okay. Now let's see. What I can see here on this elevation view is I can see a normal vector. We know our tangent is coming out towards us. There's a third orthogonal vector, isn't there, for axis system, which would be which way? We got one to the right, got one coming out towards us. Got to be one either up or down, doesn't it? Yeah. So if I call Z the traditional up, then we could put a K hat on there, couldn't we? Upward? Okay, so let's do that. K hat. In our picture here, K hat is coming up towards us in our plan view. Right. So that's a nice little triad with these three orthogonal vectors. Okay, good. So if we do the tangential forces equals mass times acceleration tangential, which is mass times the rate of change of the speed, v dot. And they told us that they're letting this thing gradually come up in its rotational omega. We're not giving that really an acceleration. We're just letting it rotate up, gradually picking up rotational speed. So in essence, then, omega is being treated as if it's constant. Okay? So we have an alpha of 0 for our angular acceleration. And this effectively is being treated as if it's constant. Okay. Down here then. What about this speed? Again, it's circular motion. Circular motion. So the speed is here with V, which is R omega, right? And if omega is being treated as constant and R is treated as constant, then that means the time derivative of this is 0. Zero. All right? Okay. So therefore, this is 0. And look at your sum of forces in the tangential direction coming out of the board. Are there any forces? No, no forces. That's nice. 0 equals 0. We like that. Okay. But that doesn't give us any additional information to solve the problem. Okay. So then, let's go ahead and why don't we look at this elevation view or the plan view and do sum of forces in the normal direction. Sum of forces normal, it looks like we have the friction force, positive friction force, times the cosine of our angle, incline angle, and be careful here, this normal reactive force from the surface has a component opposing the normal direction. So it's n sine theta, and that's a negative. And I think that's it. Sum of the forces. And that's going to be equal to the mass times the normal acceleration. And the normal acceleration we know is r omega squared. Where's our r on this picture? Is it this? Is this our r?
No, it's between the block and the
Center of the axis.
The rotational axis. This is r. right there. That's R, off the rotational axis. Always think of the path being followed by the particle. The path being followed by the particle. Okay, now add impending motion. This becomes our mu normal. Right? Okay. So let F equal mu static times the normal. And let's go to the other board. And we could factor out that normal. And we're left then with the mu static coefficient cosine of theta minus sine of theta has to be equal to the mr omega squared. I think so. And that should be about where we are here with this material, I believe. Yes.